Okay, so I'd like to begin this second lecture by running through very quickly the slides that I already showed you in my last lecture. Just take a minute or so to refresh your memory as what we saw last Thursday. Okay, so we saw this guy, and we saw a bit of Java, we saw a bit of Haskell, and we saw that Lambda calculus is rather simpler. In fact, it's the simplest programming language in the world, and you can use it when you're studying other programming languages. Features thereof. We focused mainly on syntax, and we saw a few examples of some Lambda terms. We saw a couple of notational abbreviations that are in common use. This one's quite straightforward, and I don't tend to use this much in the slide. This is a common place to get caught, okay? Because when we later will try and do beta reduction on terms like this, you have to remember this rule very carefully, because if you look at terms like this, you may think that you could take this as your argument and this here as your function. But you can't, because the bracketing has to go around here, which means that this is not adjacent to this argument. This is not an argument of this function, because there are extra brackets around here that are not shown. So always bear that in mind. I remember getting that wrong hundreds of times. And we worked out a way of notating the free and bound variables. We had the set of free variables. And then we came on to alpha equivalence, so the idea that you can rename bound variables whenever you like. We saw it in the context of Java. You can see my pretty animations now, by the way. Make sure you appreciate those. And we tried out some alpha equivalence examples. Some of them didn't work very well. Others, with a bit of work, we could make them work. And we saw the proper official definition of alpha equivalence. The complicated case was the one where we were trying to find whether two functions were alpha equivalent, and what we had to do there was pick a new fresh variable for the binding variable there that didn't occur in M or N, and then do some substitution, replacing Z for X and Z for Y in the two M's and N's. This capture avoiding substitution here gave rise to a whole load of further complexities. We learned, for instance, that when you're doing substitution, you have to make sure you only substitute the free variables, so not these binding E's here in this little Java snippet. And we also worried about capture happening in substitution. So this was the case where we wanted to substitute 4 times y in for x over here, and we worried that when we moved it over, the animation, then y there got captured. So we put it back, we changed this y over here to a z, and then we can do the substitution and all is fine. And we saw the proper definition of substitution, which was rather complicated, but it simply put into formal maths those ideas that we'd seen in the previous slides. That brought us to the end of the syntax section, except for a bonus thing, which was on De Bruijn indices. So I said that you can use alpha equivalence, rename alpha up to alpha equivalence whenever you like. You don't have to ask permission. For the rest of the course, we're just not going to worry about alpha equivalence. And one of the justifications for not worrying about alpha equivalence is that there exists another way you could encode your Lambda terms using De Bruijn indices, where you just don't bother to give names to bound variables whatsoever. You simply capture the binding pattern using arrows rather than names. Or if arrows are too graphical for you, then you can use numbers to say how far away the binder is that you want. And so this was the system due to Mr. De Bruijn. So that was the syntax section. We had a silly comic, and then we then the batteries ran out. And then we moved on to the semantics. So we saw a bit of Java semantics, saw that was very, very complicated, because this was just a tiny fraction of it. Lambda calculus semantics, rather simple. The only real rule is this one, beta reduction. And this was where you were reducing a regex, so a something of the form lambda x dot something applied to some argument. You can substitute in that argument, so you can substitute the actual parameter in for the formal parameter in M. So next time you're doing some programming and you have some function call and you go ahead and sort of apply that the argument for the function and just replace that function call with the result of the function, you can tell your friends that you've been doing some beta reduction and they'll think you're very clever. There are some other rules that basically just capture the idea that you can do beta reduction deep inside some term. Wherever you find the regex, just go ahead and beta reduce it if you like. And there was another rule that said do alpha equivalence whenever you like, but we already said that we're not going to worry about alpha equivalence. So these rules are just not very interesting. And we saw an example of beta reduction, and we saw that there's one path that you can do, and you end up at somewhere where you can't go any further. And in fact, there are several possibilities, but we did note that however you did it, we always seem to be ending up at the same result, at least on this example. And so what this led us towards was the Church-Rosser theorem, which needs, as a little bit of housekeeping, we needed a way to refer to chains of beta reductions. So this asterisk denotes a sequence of 0 or more consecutive beta reduction steps. And so using that, we could phrase a nice theorem due to Church and Rosser that says if you start at some lambda term, say m, and then you step off for 0 or more steps in one direction to get m1, and alternatively you went off in a different direction to get m2, then Church-Rosser says it's always possible to reconverge downstream, as it were. And we saw this in a nice diamond-shaped picture. So these dotted lines so the solid lines are saying, I choose to go off towards M1 or I choose to go off to M2. And then the dotted lines are saying there exists some path that will get you back so you can meet again. And we noted that it's quite important to use that chain of beta reductions language rather than just saying a single step at a time. Because, of course, here we take one step in this direction, we take one step in this direction, but in order to converge again from here, we actually need 2 steps. So it's not enough to just talk of one step, one step, one step, one step. You need multiple steps. So I think that was around where we got to last lecture. So I'll now plow on. So beta normal form, it's a pretty simple concept. This is the idea of you can't go any further. In other words, there are no redexes. There are no further opportunities to do beta reduction. And we'll say that a term has a beta normal form if it reduces eventually to something that is in beta normal form. And there's a nice theorem that says that if you have a normal form, say n1, and you have another normal form, n2, then in fact those 2 normal forms have to be the same. In other words, normal forms, if you have one, your normal form is unique. And this is a theorem that is actually very easy to prove. It's one of the many consequences of the Church-Rosser diamond theorem. And the proof goes like this. We start at m, we take a few steps in one direction to get to n1, but we also take a few steps in a different direction to get to n2. Church-Rosser says that in 0 or more steps from n1 and n2, we will be able to converge later on at that downstream point. But we also know that n1 and n2 are in normal form, which means they don't admit any further beta reductions. So when I said 0 or more steps from both of them, it must have been 0 steps in both cases. And so if you can beta reduce in 0 steps from n1 and n2 both to n, well, yeah, you get the point. They must all be equal. Sorry, that flashed up too slowly. Too quickly. so another concept that's quite important is beta equivalence. So we've seen one notion of equivalence between lambda terms already, that's alpha equivalence. Alpha equivalence isn't a very interesting notion of equivalence because it's very, very restrictive. Only very few lambda terms are included in alpha equivalence. All you can do is change bound variables. Beta equivalence is a much broader notion of equivalence, and it's obtained from beta reduction. So the concise but perhaps a bit cryptic definition is that it's the smallest equivalence relation that contains beta reduction. Equivalence relation, if you'll recall, is a relation that is reflexive, symmetric, and transitive. Beta equivalence is the smallest such relation. In practice, what this means is if you can go from, say, M1 via a chain of beta arrows pointing either left to right or right to left, so in either direction, any chain of forwards and backwards beta reductions to get over to some other term, then M1 and M5 are beta equivalent. So where alpha equivalence is sort of capturing lambda terms that sort of look the same, I guess, beta equivalence is capturing lambda terms that sort of behave the same. Okay. Unfortunately, beta equivalence as defined like this is not very, it's not very useful. And the problem is, because it doesn't really tell me, I mean, suppose you give me two lambda terms and you want to know whether they're beta equivalent. I've said that they're beta equivalent if you can construct any chain of forwards and backwards beta reductions between them. But there are quite a lot of these chains. And in particular, if I suppose the term that one of the terms is M1 and the other one is M2, I might say, okay, so I've got to try and find a chain. Maybe I will do a backwards step first to that guy. That's certainly a true beta reduction. You can certainly M1 applied, so given as the argument to the identity function, will certainly give you M1. But you can see I haven't really made much progress here, and indeed I might be rather silly and think that this was a good strategy. And carry this on rather indefinitely and never make any progress at all. So the problem with talking about these unconstrained chains of beta reductions is that you can basically do beta reduction in reverse forever. So a more practical definition to actually that actually suggests an algorithm for checking whether two beta terms, whether two lambda terms are beta equivalent, is again to think of your Church-Rosser and look at this diagram and remember that whenever we have a shape like this, we can always close off the bottom half of that diamond like that. And so, and we can do this whatever this shape is, we will always be able to go down, 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 down to some point down here, down, 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 down from the other side, down to some point down here. So the simpler version that's more practical is that M1 and M2 are beta equivalent if there exists some other term that is downstream from M1 and it's also downstream from M2. Yeah? Okay, so that is several key concepts, most of them beginning with the letter beta. So beta reduction, confluence, this Church-Rosser theorem that keeps cropping up. Beta normal form, so this sort of captures the idea of something being a value, really, so not something you can't execute any further. And beta equivalence. So moving on then. One of the things I mentioned earlier was, I said, if a term has a beta normal form, that normal form is unique. But I said if. And you see, the thing is, there are some terms that don't have a beta normal form. and you might like to think in your own time what this analogy might mean in a language like Java. So an example of such a term is lambda x dot xx applied to lambda x dot xx. You see, if I try and beta reduce that term, the only beta reduction I can do is this argument in for this parameter x here. But if we see what's going to happen, that argument is going to go in here and here, so 2 copies of that argument, and it's actually beta reduced to the same thing. I think that's really cool. And of course, you're going to carry on forever, right? That's not in beta normal form, because you can carry on beta reducing, but you're never going to get anywhere. Got a sort of non-termination kind of thing going on here. Some terms might not terminate. So consider this term. What we could do is take this as the argument and substitute that in for x. Well, this function here ignores its argument and just returns y. So that would just give us y. That would be one thing we could do. But another thing we could do is we could try and beta reduce inside here. Well, we've seen what happens when we do that. We just get it itself. So this term will either beta reduce to itself or to y. And we can carry on. So at any point, I can either terminate or carry on forever. This is a lambda term that might not terminate, or it might terminate. And it depends, you can see, very much on what strategy you use for doing your beta reduction. So let's look at reduction strategies. Suppose I have a lambda term that looks like this, so a redex, basically. There are a couple of things I could do as part of my strategy. I could say, right, go ahead and substitute that argument n in for x. So do the beta reduction straight away. That's one thing I could do. Another thing I could do is I could see, are there any redexes deep inside n? I could tackle those first. And there's a third option. I could see if there are any redexes deep inside m. These are the 3 broad strategies. And it turns out that they all have a name. This first one, this is called call by name. This is used in Haskell-ish. So there I make no effort to reduce the argument. I just go ahead and substitute it into the function, and I hope that the function will sort of take care of reducing it later on. Or call by value, this is where I will fully evaluate the argument to the function before actually substituting it in. So this happens in Java or C, most languages. Or I could reduce M. This doesn't really have a name, and this doesn't really happen in any language. You don't, in practice, evaluate the body of a function before that function has actually been given its arguments. That would be weird. That doesn't happen. You could do it, but... And so this now is going to be a slightly technical slide, and all I want to do with this is show you how you can take these very general rules for beta reduction. So these are all of the rules for beta reduction we saw a few slides ago. And I just want to show you that by making restrictions on when you apply these rules, you can obtain call by value and call by name. So this down here is your main beta reduction rule, and then these 3 rules are the rules that say you can do beta reduction inside a function body. Yeah. This is saying you can do beta reduction on the left-hand side of a function application. And this is saying you can do beta reduction inside the argument part of a function application. So to get call by name, I throw away this rule. This was the rule that said I can reduce inside a function body, but we said we don't want that. We throw away this rule that says I can reduce the argument. Well, we don't want that for call by name. And so that just leaves us with this rule and the main beta reduction rule. So this rule, it looks a bit like you're reducing the body of the function. You're not. All you're doing is you're reducing m enough until you get m into this shape, lambda x dot something. And then you stop and you apply the function. Okay? So I'm calling it beta n for call by name. Then call by value, you can also get very much the same. We don't reduce inside a function body, no rule there. We reduce the left-hand side of an application, same as call by name, because we want to get the function here into the shape lambda x dot something. And so that's this rule here. And then we have an extra rule in call by value that tells us to evaluate the argument. So we're saying as long as the function can't be reduced any further, i.e. we've got the function ready in this form, then you turn your attention to the argument. So evaluate the argument, n. And once the argument can't be reduced any further, and the function is in the right form, then go ahead and do the substitution. So that's call by value. So simply by restricting, adding extra conditions on these beta reduction rules, we obtain a reduction strategy. And going back to our running example of this little lambda term here, if you were to take the call by name strategy from this point, then you'd end up following this path. And if you followed call by name, call by value, then you'd follow this path. Okay. It's interesting to note that there's a difference here. Call by value only takes 2 steps, right? Call by name takes 3. So in a sense, call by value is a bit more efficient computationally, right? So maybe our programming languages should use call by value rather than call by name. Now I mentioned that call by name is used in Haskell. That wasn't quite true. Haskell uses call by need, and this is the essence of it is the same as call by name, okay? But it has an extra efficiency hack, basically, that means once an argument has been evaluated, you don't need to evaluate it again. It's called memoization, if you like the jargon. And so the thing that makes call by name slow here is that we've got this fairly complicated argument here that we're passing in, and we're using it twice. And so the fact that we're using this argument twice here means we have to evaluate it twice here. So here I'm evaluating the first occurrence of that argument, and then I evaluate the second occurrence of that argument. But these 2 steps are basically doing the same thing. So it's a bit repetitive. Whereas call by value, you evaluate the argument, and that's done now. That's got you down to y, and then you just substitute it straight in. So perhaps call by value is the way forward. Not so fast. Call by value also gets us into sticky situations like this. See, call by name would say, well, I don't want to evaluate that argument. I'll just substitute it straight in. And if you do that, then you would realize that this function, although it takes an argument x, it actually just throws it straight away and just returns you y. Call by name then would give you y. But call by value, because it's so eager, it has to evaluate every argument regardless of whether that argument is going to be needed. So call by value will take you down here and on to infinity. So the lesson is, call by name will win if the argument is not used, and particularly if that argument would turn out to be very computationally expensive to evaluate, or even not terminate at all. On the other hand, call by value will win if your argument is used more than once in the function body. Now, in practice, most functions that we write do use their arguments. I would postulate. I don't think there's many occurrences where you take an argument and then just ignore it. So in practice, I think call by value is probably more efficient. Right. So it's 10 o'clock. I think I will do one more slide, and then I'll give you a 10-minute break, because you've been here for an hour, so that's okay. So one last slide is a bonus slide, so just for your intellectual development. I wanted to talk a tiny bit about philosophy. This is the principle of extensionality. So consider a mathematical function or a computational function, doesn't matter. In fact, consider two of them. And you want to know whether these two functions that you have in your hand, are they the same function? Now, if you're an extensionalist, then you would say, well, I can tell if these two functions are the same or not, because if I give them the same inputs, I will always get the same outputs. So, in other words, you're treating the function like a black box. You're just looking at what you give into it and what you get out of it. An extensionalist would say that that's enough to say that the two functions are the same. An intentionalist, the opposite, would be somebody who would say, well, I'm still not convinced. I actually want to unpack this box, this black box that contains the function definition, and look at how these functions are defined to see whether they're the same. So that's a little bit of philosophy there. Now, how does this apply to the Lambda calculus? Well, we might question whether beta equivalence is the best notion of equality between Lambda terms. And one of the shortcomings of beta equivalence is that it does not say that these two terms are equivalent. This is the term that says it's the function that takes x and returns sine of x, so mathematical sign. Should that be treated as the same function as sine? I mean, morally, this feels like they should be sort of the same, and indeed, from an extensional point of view, they are, because if I give them the same input, say any term m, if I give m to both of these terms, then they are beta equivalent, because in one step, this m will substitute in for x, and we'll get sine of m. That's the same as sine of m. So if you take an extensional point of view, beta equivalence isn't quite enough. However, we can fix this if we just add an extra notion of equivalence. This is called eta equivalence, so we're really getting through the Greek alphabet now. Eta equivalence simply says that this term, which has this shape up here, so lambda x dot m of x, where x is not free in m, that term is eta equivalent to m. Okay, so we're basically just adding this as an extra point where lambda terms are the same. If we add that into beta equivalence, then we get beta eta equivalence. Okay, so just all of these notions of equality just jumbled in together, and now we've got a nice notion of equality that includes extensionality. Okay, I'm going to stop there, and so let's reconvene at in 10 minutes. So I make that 10:14. Okay. Okay, let's start again. So I've got one more bonus section. I think this is great fun, but yeah, I'm afraid it won't be exam level. So we talked quite a bit about this Church-Rosser theorem, and I wanted to make a few remarks on how you go about proving it. So to recall, the Church-Rosser theorem is all about saying, does beta reduction satisfy this property, that if you start at this point, you wander off this direction for a few steps, wander off this direction for a few steps, can you always later take 0 or more steps to reconverge? How do we prove it? So it's hard to prove, and the main reason why it's hard is because of these asterisks here. You have to, the theorem has to hold for taking any number of steps in this direction and any number of steps in this direction, and it's quite hard to consider all the cases. So perhaps we can prove an intermediate step that will be a bit easier. So perhaps we can go and find this. Perhaps we can show that beta reduction satisfies diamonds of this shape, and then go on to generalize to this shape. See, this latter step is quite easy. You can visualize this. It's just filling in the tessellating these diamonds like this, and then you'll get the multi-step piece nicely. But unfortunately, as you probably remember from the slides, beta reduction doesn't satisfy this property, so we can't use this as an intermediate step. Okay, remember, sometimes you can take one step in this direction, one step in this direction, but then it takes maybe 2 or 3 steps from this side before you can actually reconverge. So we don't have this intermediate state here. So second attempt is to say, we'll go from beta reduction. Can we get to this pattern here? Can we say beta reduction always satisfies that if you take one step in this direction, one step in this direction, and if you allow several steps, then we can reconverge. Beta reduction does have this property. You're sensing a but. You don't have this step. If you have this property, you do not necessarily have this property. I think it's a bit fascinating because that looks like it just be true. It's not. So if we call that property A, that one property B, turns out that there are some relations that satisfy property A but don't satisfy property B. And one of those relations is this one. It's simple enough geometric map. We have property A because if you take an arbitrary point, say that one, up there, and you take one step in 2 different directions, getting to there and there, then it's obvious that you can reconverge if you have 2 steps, like that. Right? However, if you allow yourself to take multiple steps, then you could go down to here, and you could go down to here. And then you'll notice that from the red point, you can only go in that path. That's the way the arrow is different. And from the green point, you can only go that path. You will never reconvert. So we can't use this as an intermediate step for proving the Church-Russell. So how do we prove the Church-Russell? Well, it's hard, and you'll have to look it up. So this brings me to the third part of the lectures on the Lambda calculus. So we've seen how the Lambda calculus looks, we've seen how it behaves, and so finally I want to say a bit about how you can use the Lambda calculus to obtain a usable programming language. I have a silly cartoon just to rest your brains for a moment after all that Church-Russell. So, the first thing that's obviously missing from the syntax of Lambda calculus is numbers. These generally appear in other programming languages. So how can we encode numbers just using Lambda type? Well, it goes something like this. We'll let 0, we shall encode as a function that takes some argument, say s, and returns a function that takes an argument, say z, and returns z. Okay, and so the notation I'm going to use is we'll have 0 is the number, and then 0 underlined is the Lambda calculus representation of that number. Okay, so that shall be 0. 1 shall be, we take an argument s, take an argument z, and return z of z. That is 1. Two is similar. Perhaps you're starting to see a pattern here. This time we apply s to s of z. Okay, so the function s is sort of being applied twice. And 3. And so in general, the mathematical number n shall be encoded as the lambda term that takes s, returns a function that takes z, and returns s applied n times successively to z. These are called church numerals, these terms of this form. They were first invented by Alonzo Church, who invented the lambda calculus. So I say that these are numbers. How can I justify that? Well, I can encode arithmetic using this. So I can have a lambda term that represents the plus operation. And that is it. I mean, what can one say about that? I mean, it's just magic. I mean, this just gives you something that behaves like plus. I mean, how could that that contrived sequence of variables, how could that possibly resemble plus? It's very odd. And even more interesting, perhaps, we could do multiply. Now, you might think, if you're thinking in terms of like digital electronics, multiply should be quite a lot more complicated than plus, right? Not. And you should see exponential. I haven't got that on the slide, but exponential is simpler yet. It's bizarre. So it's very difficult. I mean, you can just like try this out. I mean, you know, one way to understand this is just to try it out. So if you just take, you know, the church numeral for 2, church numeral for 3, plus you've got all the definitions, just, you know, fire up your beta reduction engine, and you'll see that this will reduce to this will be beta equivalent to the church numeral for 5. And you can try this, and this will be equivalent to the church numeral for 6. It just works. I want to try and give you a tiny bit more intuition than that, though. And so if I just go back a bit, you'll note that I called this S and Z, which isn't that's not my normal choice for parameter names. Usually I use X and Y. And perhaps if you think back to when you were learning Haskell, perhaps, and perhaps discrete mathematics, you learned that natural numbers can all be encoded just using 0 and the successor function. So 3 is the successor of the successor of the successor of 0, right? Successor of the successor of the successor of 0. So in a sense, what's sort of happening here, and it's all very hand-wavy, but what's sort of happening is that with the church numeral, we are encoding it as a function where if you tell me what you mean by the successor function, and you tell me what you mean by 0, then I will apply your successor function the right number of times to the 0 that you gave me. So then with plus, what happens is, so I should say, this is the function that takes the first church, so n is going to be a church numeral, we assume. N is also assumed to be a church numeral. And so this then is the church numeral that is the result. So because all church numerals take the shape successor and 0 and then something. And what we're doing is we're supplying to the church numeral m, we're keeping the successor function as just x. But rather than passing m 0, we're passing it basically n with the successor in 0. So it's like saying, it's saying apply the successor m times, but don't start at 0, start at n. Well, that's going to give you, in total, the successor will be applied m plus n plus m times, if you You just offset it. Yeah? Sort of makes sense. And multiply, we do a sort of similar trick, except multiplying, we don't modify what the 0 is. We keep 0 as just 0. But this time, we're modifying what the successor is. So this time, rather than when we sort of evaluate m with the 0, except rather than passing m just the successor function, we apply the basically n times the successor function. So rather than doing successor m times, we do add n m times, and that gives you multiply. Okay. So I think to get further understanding beyond that, I think you just have to evaluate these terms and just see, oh yeah, this sort of seems to be working. So plus and multiply, these are ways to take numbers and sort of build new ones, sort of constructing numbers, as it were. We can also sort of go the other way, as it were, and deconstruct numbers, which is to say test whether a number is 0 or not. So this term here, if z, this is short for if 0. And the idea is if 0 will take 3 arguments, a church numeral n, and then the intended behavior is that if n is 0, then I want you to evaluate x1. And if n is not 0, I want you to evaluate x2. So it's basically it's an if then else, right? It's if n equals 0, then x1, else n equals 2. And this again is fantastically concise. I mean, yeah, I'd have thought that with the lambda calculus syntax being so primitive, you'd expect that the terms would have to be huge. But it's not the case. It's so concise. How is this working? So we're passing to the church numeral n. This is the sort of successor function thing, and this is the 0 sort of thing. And you'll remember that if n is 0, it's the function that just returns 0. So you'll get, if n is 0, it will just return x1. Good. And if n is not 0, then it will call the successor function at least once. Okay, successor of something. And the thing about this successor function is it's one of those functions that takes an argument and then ignores it. It's just going to return x2. So what this means is if you call the successor at least once, you're going to get x2 out, no matter how many times you call it. And that's exactly what we want. Isn't this cool? As an exercise, so you can go further. So we've seen how to do plus. You can also do predecessor. So this is subtract 1. Okay? So we want some term that's predecessor of 0 should give us 0. So it should be beta equivalent to the church numeral for 0. And the predecessor of the church numeral of n plus 1 should be beta equivalent to n. That's the specification for that term. I'm not going to tell you what predecessor is. It turns out that some of these functions, like plus, multiply, and if 0, these work out really rather concise. And unfortunately, predecessor is just one of those functions that it doesn't make the lambda calculus look good, put it that way. In fact, when the lambda calculus was first developed, Church, I think it was, thought that it was actually impossible to write the predecessor function. That's how hard it was. And it wasn't until his PhD student, Stephen Cole Claney, I think, who later became a very famous mathematician and magician in his own right, he was having his wisdom teeth extracted, and that was the time when he sort of had his eureka moment for how to encode the predecessor function. So it is possible, but I'm going to leave it as an exercise. It's rather hard, but it can be done. So it's now 10:30. We have tomorrow as well, or part of tomorrow. So tomorrow is, so Philippa will be back, and it will be partly revision and discussing what's examinable in this course, and a little bit more of this sort of stuff. We're going to encode some further. What are we going to do? So there are a few more language constructs that are quite interesting to see how they're encoded in the Lambda calculus, and we'll do a sort of a real life example of a serious piece of code, 2 lines at least. So that's going to come tomorrow, and for the remainder of this session, so the next 20 minutes, we're going to do some more tutorial